Let us further discuss vector spaces. Two of definitions which are very important with respect to vector spaces are linear combinations and spans. We'll first discuss linear combination. Linear combination of vectors is, as the name suggests, combining the vector in a linearly fashion and multiplying every vector with a scaling factor. So imagine we have got vector v1, v2, v3 up to vn in a real space of n dimension. So a linear combination would be c1 v1 plus c2 v2 plus c3 v3 up till cn vn, where c1, c2, c3 up to cn are member of real set. Or in other words, c1, c2, c3 up to cn are all real. The combination of vectors give us another vector. So if we add all these vectors, which belong to Rn space, we will get another vector which also belong to the Rn space. Now let us further explore this idea by taking two vectors. Imagine we have got two vectors v1 and v2. Vector v1 is shown by a red arrow having components 4 and 6, and vector v2 is shown by a green arrow having components 4 and 2. Vector v1 and v2 can be linearly combined, and we can get any vector from that within the E1, E2 space or within R2 space. So the resultant of these two vectors is a blue vector whose components are 8 and 8, and we get them by adding v1 plus v2. Please notice that this is also a type of linear combination where the value of c1 and c2 is equal to 1. In other words, if in the linear combination equation, if we take c1 up to cn equal to 1, then it will give us the resultant of all the vectors within a space. However, the linear combination definition is broader than the simple resultant definition. Linear combination is telling us that if we combine the vector, any vector, number of vectors within a real space, we can get any vector within that space. This brings us to another definition of a vector space, which is span of a space. So span of two vectors is equal to R2 space. Taking the example of the same two vectors, v1 and v2, we can also say that span of v1 and v2 is equal to R2 space. This is another way of saying that the linear combination of v1 and v2 will define another vector or any vector within the R2 space. Now, what will happen if we have a vector lying along a single line? So imagine if we have a vector along E2 or any vector along E1. In that case, the span of both the vectors will be equal to R1 space. This means to say that any two vectors which are lying along one line, any combination of them will give us a vector which will lie in the same along the same line. Imagine we have got this vector whose dimension is 4, 2. We can draw another vector which is having the same magnitude but opposite in direction. So the component of this black vector would be -4, -2. Now, if we take combination of these two vectors, it will give us all the vectors which are along this line or which are collinear to this line. So based on that, we can say that the vector v1 and v2 having components 4, 2 and -4, -2 is in R1 space. So the span of these two vectors is in R1 space. Similarly, if both the vectors are 0, 0, then our span is equal to R0. Now, just to demonstrate how we can get any vector from combination of V1 and V2, we can write this in a simultaneous equation form. So C1 multiplied by the component of V1 plus C2 multiplied by the component of V2 is equal to any vector W1, W2. This is a general vector which can be anywhere within E1, E2 space. We can determine the value of C1 and C2 in terms of W1 and W2. Please note that W1 and W2 are the components of vector W. That's why I'm removing the underline which shows a vector. Once we have found C1 and C2, they can be correspondingly multiplied with V1 and V2, and we will get the required W1, W2 components. So this small example tells us that by taking combination of V1 and V2 and multiplying appropriate scaling factors, we can get any vector in the E1, E2 plane. Now, the last question which one might ask is that where can we use these ideas in structural mechanics? So in order to demonstrate that, let us assume that we have got a shell roof which is made up of a nonlinear or a curved path and a linear path. So there is a kink in the roof. Now imagine we have load applied on the kink. If we are carrying out structure analysis or we want to design this shell structure, we would be required to find out the tangential forces along both the curves. So we can find out the unit vector along the tangent line of both the components and then multiply appropriate scaling factor to them so that we can get the red vector as shown over here.